Section 7.2 continued, dividing radical expressions. And the property is the nth root of a and the nth root of b are real numbers and b can't equal 0. Remember, the key is that my index for each must be the same value. And if that's true, I can have the nth root of a divided by the nth root of b, and I can rewrite that as the nth root of a over b. In other words, I can put the quotient under the same radical with the same index of each of these two. But the best power of this is, whether I can rewrite it or not, is that I can just simplify it as it was if it was rewritten. In other words, I can simplify the quotient of a over b and leave it separate if I want, or I can leave it under one radical. Whatever it turns out to be easiest to solve the problem. After I do simplify, and if there's a radical in the denominator, remember I can't have a radical in the denominator. Therefore, to eliminate that radical in the denominator, I'm going to rationalize. And if it's a square root, I'm going to multiply the numerator and denominator by that radical in the denominator. If it's an nth root, I'll have to do a little bit more work to multiply the numerator and denominator to eliminate that nth root in the denominator. Here's an example. Here we want to simplify each expression. I have 4 square roots of 8 over the square root of 2. Since my index is the same, I can rewrite that as 4 square roots of 8 over 2. But the quickest way to perform this operation is, as I said on the previous slide. I know this is true, therefore I could just rewrite it as 4, and knowing that I have 8 divided by 2 is 4, and that has to go under that radical. So I know I can go from here right to here. If I want to, I can rewrite it this way, and then that would put me back down to here, but this is just quicker. Now I know the square root of 4 is 2, 2 times 4 is 8. Here I have 4 square roots of 6 over 3 square roots of 2x. I know I can rewrite this as still 4 over 3, and I could rewrite it as 6 over 2x under one radical. If I did that, I could then still simplify, but I could still simplify here knowing that 2 goes into 6, which would leave me the square root of 3 in the numerator. The 2 would be eliminated in the denominator, and just leave me the square root of x. To me, that is a lot quicker, knowing that I could rewrite it under one radical, but keeping them separate. Now, that keeps me realizing that I need to rationalize because I'm not allowed to have a radical in the denominator. So I'm going to multiply by the square root of x over the square root of x. 4 square roots of 3 times the square root of x. I use my product rule, 4 square roots of 3x over 3 square roots of x squared. And when I simplify, 4 square roots of 3x over 3 square root of x squared is x. And these two values cannot simplify because the numerator is under a radical while the denominator is not. Again, I want to simplify. Here I have the values under one radical. I kind of prefer them separated. So if I can go from here back, I can go here forward. I can take it any way I need to have it put to simplify the problem. Now I notice that I have a radical in the denominator. Rationalize by multiplying by that radical in the denominator gives me 8, which I'm going to write as 4 times 2 square roots of x, all over the square root of x squared, which when I simplify gives me 2 square roots of 2x over the square root of x squared is x. Again, we want to simplify each expression. Here I have a quotient, the square root of 3x to the 5th over the square root of 6x cubed y to the 5th. We know from our quotient property of radicals that I could write this under one radical. Instead, I'm just going to keep them separated, but knowing I can do that allows me to simplify within the radicals. Therefore, when I do that, I will have a square root on top and a square root on bottom. The square root on top will be 3, and 6 will simplify. That will give me a 2 on the denominator. X to the 5th on top, x cubed on the bottom gives me x squared in the numerator, and y to the 5th in the denominator. Now I need to rationalize to eliminate the radical in the denominator. To do that, since it's a square root, I just multiply the top and bottom by that radical in the denominator, which is the square root of 2y to the 5th over the square root of 2y to the 5th. Multiplying the numerators across is going to give me the square root of 2x squared y to the 5th over the square root of y to the 5th times the square root of y to the 5th is the square root of 4y to the 10th, which when I take the square root of that is going to give me 2y to the 5th. And I cannot simplify any further because the denominator is not under a radical of the same index. Therefore, this is my solution. And on this problem, I want to simplify the expression. I have 1 over the cube root of 2x. I will not simplify any further since it is in the simplest form, but I'm not allowed to leave it in this fashion because I have a radical in the denominator. So I do need to rationalize. On our previous examples, and even from the quotient property page, I stated that if it's a square root in the denominator, I multiply the top and bottom by that square root. Unfortunately, I don't have a square root, so I have to eliminate this radical by rationalizing, and it must be of the same index, so I need a cube root. So I need to determine, when I multiply these two radicals together, what value will eliminate the denominator value for the radical. So how I would do that is to multiply 2's by some number that I could take a cube root of it and get a whole number out of the radical. That would be multiplying it by 4. 2 times 4 is 8, and the cube root of 8 is 2. I would multiply the variable by x squared, because x times x is x cubed, and the cube root of x cubed is x. That would eliminate the radical in the denominator. And I can perform this operation because as long as I multiply the top and bottom of my fraction by the same value, it just changes the look of the fraction, but not the value of the fraction. So I'm going to multiply the top by the cube root of 4x squared. Now I multiply across, that gives me the cube root of 4x squared in the numerator, and in the denominator, that's going to give me the cube root of 8x cubed. But I know I can simplify the denominator, so I still have the numerator, the cube root of 4x squared, over the cube root of 8 is 2. The cube root of x cubed is x. In our next example, we have 1 over the 4th root of 9x to the 6th. We can't simplify any further in our fraction, but we need to rationalize to eliminate the radical in the denominator. To do that, I'm going to multiply, of course, by a radical. I need the 4th root, but I need to multiply 9 by some number, so when I take the 4th root of it, it becomes a whole number out of the radical. That would be 9. 9 times 9 is 81, and the 4th root of 81 is 3. I need a exponent that's divisible by 4. Therefore, to do that, I'm going to multiply x to the 6 times x squared, because x to the 6 times x squared is x to the 8th, and the 4th root of x to the 8th is x squared. Let's multiply across. That's going to give me the 4th root of 9x squared over the 4th root of, and we could do this in your head, but I'm going to show you. 9 times 9 is 81. X to the 6 times x squared is x to the 8th. Then we simplify the numerator, the 4th root of 9x squared, over the 4th root of 81 is 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. And the 4th root of x to the 8th is x squared. And that's my solution. In our next example, we have a binomial in the numerator and a radical in the denominator. I want to simplify by rationalizing the denominator. Since it's a square root, I'm going to multiply the top and the bottom by the radical in the denominator. Since this is a binomial in the numerator, what I have to do is to distribute the square root of 6 through the binomial. Therefore, that's going to give me 3 square roots of 6 plus the square root of 6 times the square root of 3 is the square root of 18 over the square root of 6 times the square root of 6 is the square root of 36, which is 6. Now I need to simplify this. The square root of 18 can be broken up. That's going to give me 3 square roots of 6 plus the square root of 18 can be 9 times 2 all over 6. That's going to give me 3 square roots of 6 plus 3 square roots of 2 all over 6. Now what I can do is factor a 3 out of the binomial. That's going to give me 3. And inside is going to give me the square root of 6 plus the square root of 2. And I cannot combine these because they're not like terms. Even though they have the same index, what's inside the radical is not the same. And this is all over 6. Now I can simplify the fraction. So that leaves me in the numerator, the square root of 6 plus the square root of 2 all over 3 and 6 simplify with 2 on the denominator. We have a similar example in our next problem. Again, I want to rationalize because of a radical in the denominator. So I'm going to multiply by the square root of 6 over the square root of 6. Since I have a binomial in the numerator, I need to distribute. That's going to give me the square root of 18 plus the square root of 48. And the square root of 6 times the square root of 6 is the square root of 36, which we know is 6. Now I need to simplify in the numerator. When I do, that's going to give me the square root of 18, which I can separate into 9 times 2, plus the square root of 48, which can be 16 times 3, all over 6. Square root of 9 is going to give me 3 square roots of 2, plus the square root of 16 is going to give me 4 square roots of 3. And that's all over 6. If you want, you could separate these into 2, but since 6 doesn't go into both of them, I will ask you just to leave it here. But if you wanted to look further, you could separate this into 2. 6 would have to go under both of these, which would be 3 square roots of 2 over 6 plus 4 square roots of 3 over 6, which then I could simplify each fraction, which would give me the square root of 2 over 2 plus 2 square roots of 3 over 3. But I prefer to leave it in this fashion. Again, we want to simplify on this example. We have the 4th root of y to the negative 8th over x to the negative 12th, z to the 4th. We know when I have negative exponents, I have to move their location. If it's in the numerator, with a negative exponent, I'll move it to the denominator. If it's in the denominator, I need to move it in the numerator. We've covered this in previous sections. So let's do that. That's going to give me the square root of x to the 12th over y to the 8th, z to the 4th. And recall that's to the 4th root. Now I need to simplify. The 4th root of x to the 12th is going to give me x cubed over the 4th root of y to the 8th is y squared. And the 4th root of z to the 4th is z.